Viewers like you make this program possible. Support your local PBS station.
What's it take to make our modern world?
Oh, that's amazing!
I'm David Pogue. Join me on a high-speed chase through the elements and beyond.
Oh my God!
As we smash our way into the materials, molecules, and reactions
It's a really cool enzyme because it makes life on Earth possible.
that make the places we live, the bodies we live in, and the stuff we can't seem to live without.
The only thing between me and certain death is chemistry?
From killer snails
Just when you think you've heard of everything, nature will surprise you.
and exploding glass to the price a pepper-eating Pogue pays.
There's gotta be some easier way to learn about molecules.
We'll dig into the surprising way different elements combine together and blow apart. In this hour, we swing from the molecular chains and surf the atomic webs that give some materials unique abilities. The moldable molasses of molten glass,
Come on!
the built-in boing of rubber,
The G-forces are indescribable.
and the menagerie of modern plastics that these days is both a miracle
Oh!
and a menace.
People want to do the right thing, but it's really difficult to know exactly what to do.
Beyond the Elements, Indestructible. Right now on Nova. Ah, the periodic table. The who's who of atoms. The stuff everything is made of. With familiar names like hydrogen, oxygen, carbon, and iron. But what if every substance were made of just one kind of atom? Just one kind of element? What if a human were made only of carbon? What if water were made only of hydrogen? And what if salt were made only of poisonous chlorine? Luckily, nearly all elements like to stick together. It's through the combination of different elements that our world exists. And we've made it an even richer place by learning to harness and even make those combinations to create new materials that have shaped our modern world, such as rubber or plastic, materials we've come to depend on, but that sometimes come with difficult environmental downsides. But let's start with one of the oldest and most chemically interesting. Look at the buildings in any city today, and you'll see, or see through, one of the signature materials of our times: glass. The Corning Museum of Glass in Corning, New York, is home to an internationally famous collection of glass, with examples that range from antiquity to contemporary art. From the functional to the fantastic. The museum also runs demonstrations of glass blowing.
She's applying glass color to that molten glass. By holding it to the ground, gravity takes hold and she gets that beautiful ruffled edge.
Some include opportunities for novices like me to get into the act.
We're going to be making something we call a Roman bottle. Good. Keep going. Keep going. All right, stop.
The kind of glass I'm working with is the most common sort. Soda lime glass, the stuff of windows, drinking glasses, and glass bottles.
Give the pipe a tap.
Woohoo! I am good at this!
Eric Meek one of the hot glass program managers, breaks down the ingredients in soda lime glass for me.
So these are the raw materials that we use to make glass. The first main ingredient is silica sand. You can see this is a beautiful white, pure silica sand. This will make really nice clear glass for us.
Silica is a network of silicon and oxygen atoms, where each silicon atom shares electrons with neighboring oxygens in what are called covalent bonds.
To get this to melt at a lower temperature, we add soda ash. So that's sodium carbonate.
Sodium carbonate, two sodiums electrically attracted to three oxygens, sharing electrons with a carbon atom.
If we melted pure silica, it would melt nearly 4,000 degrees. If you add soda ash, it drops the melting temperature down to around 2,000 degrees Fahrenheit.
So easier for us to bring about.
Easier for us to bring about. And then the final ingredient over here is crushed limestone or calcium carbonate.
Like sodium carbonate, but with a calcium instead.
Calcium carbonate will help to stabilize the glass over time.
Wow. And you just sort of mix that up in a pot and
Yep.
put it over a medium flame and
It's that easy. You mix these together, put it in a crucible, melt it at about 2,000 degrees, and you have glass.
At high temperatures, all those powdery ingredients melt together to form a viscous liquid that cools into glass. But there's more to the story. Most solids are crystalline, like frozen water, the ice in your glass. In ice, the water molecules are arranged in a regular pattern. If we heat it to its melting point, ice quickly turns to liquid, with water molecules sliding past each other. And then, if we drop the temperature, the water refreezes, and the regular crystalline structure of ice returns. Silica sand, the primary ingredient in common glass, typically also has a regular crystalline structure. As you heat it up, it too will melt just like ice does, more or less all at once transitioning from a solid to a liquid, with the network of silicon and oxygen atoms sliding around chaotically. But this is where glass gets weird. When you cool our liquid silica down, it doesn't find its way back into a crystalline structure. Instead, it becomes an increasingly viscous liquid with jumbled rings of atoms. When it finally cools down enough, that warped, irregular structure becomes locked in place into what's called an amorphous solid. The range of temperatures in which glass remains a viscous, goopy liquid that we can manipulate is one reason it's such an important material and has made possible the amazing art of glass blowing. When most of us talk about glass, we mean silica-based glass, ordinary glass. But glass is also the term scientists use for any material that exists as an amorphous solid. Materials that, unlike a crystal, have an irregular structure, and when heated, pass through a phase that's not exactly liquid and not exactly solid. A phase I call gooey.
So glass comes in many forms.
Eric Goldschmidt, a flame worker, demonstrates that glass doesn't have to be, well, glass, using a piece of hard candy.
And it actually acts a lot like glass that we use out of our furnaces here. So I'm softening this material with some heat, getting those atoms moving around, and it simply will never have the opportunity to come back to a crystalline network. So we can soften it a little bit, start to inflate it.
start to inflate it. Come on. Dude, you're making a Roman bottle out of a Jolly Rancher.
Theory can be shaped into just about anything because of its ability to sort of transition from really fluid to fairly rigid.
Would this still taste like candy?
I don't think we've cooked the sweetness out of it.
Is it too hot?
It should be cool enough to touch.
Excuse me. My gosh, I feel like I'm eating the wrapper. I've never had candy that light and flaky.
And I don't think I've ever had anybody eat a piece of glass that I've inflated either.
This is gorgeous. This is clearly going to be worth something.
Straight out.
Okay.
Yep, there you go.
Maybe if I stopped talking and kept working. There's an underappreciated aspect of glass blowing that I learned about firsthand.
There we go, comes right off. So
After you shape a piece of glass while it's hot, it has to cool slowly in an annealing oven that gradually ramps down the temperature. For something this size, it takes about 12 hours. Otherwise, differences in thickness mean differences in cooling, leading to stresses that can cause the piece to crack. But what happens if you cool some glass really fast? Then you get these, Prince Rupert's drops, named for Prince Rupert of the Rhine, who brought them to England in 1660 as a scientific curiosity.
So I'm gonna have you take this hammer and try to break this drop.
Are you nuts? It's glass.
All right, so just grab it down here by the tail, all right, and set it down there on the table, and just make sure you hit the thick end.
Just shatter it?
Yep.
Come on. No! Oh no! I broke your table! That's insane. We've established that this glass is indestructible. Congratulations.
We have, but there is an Achilles heel. There is a way to break this.
Considering that this glass just dented a steel table, I'm skeptical.
So snap it down on the tail.
This is me trying to snap off the tail of this unbreakable glass. What? Where'd it go? It's gone. What just happened? Well, let's rewind a little. To the key moment, when the drop of hot glass enters the cold water, the outside of the glass immediately cools and locks into shape. But the inside cools more slowly, gradually contracting, trying to pull in the rigid outside glass, creating a tremendous amount of stress, placing the outer layer under compression.
A lot of materials under compression are very strong, including glass.
So strong, you can't break it with a hammer. But there's an Achilles tail, because that part is so thin, when it enters the water, it cools just about all at once. No compression effect, no super strength. I can break it with my hands. And that surface fracture races through the rest of the compressed material.
Once that compressive layer is compromised, there's so much energy in there, the whole thing will crack.
Kablamo! Total drop destruction. Turns out the surprising strength of a Prince Rupert's drop plays a role in how we make glass today. Manufacturers take advantage of the strength of glass under compression to make a special kind called tempered glass.
So this is a piece of commercial tempered glass, and rather than being cooled with water, this one is just cooled with jets of air on the surface. The jets of air sort of make the skin of the glass rigid and stiffens the surface of the glass. The core of this cross-section is left to cool a little bit more slowly, and so it pulls away from the surface, and that creates a compressive layer on the surface.
So it's sort of compressing itself from the inside.
From the inside, exactly.
So then, what is this, like Prince Rupert's sidewalk? It may seem counterintuitive. Every cell in my body is saying this is a bad idea. But by cooling the glass to create compressive stress, generally more than 10,000 pounds per square inch, it becomes physically stronger. I can walk, even jump on this tempered piece that's about a half-inch thick. Oh my gosh. Ah! What? They can make diving boards out of this stuff. Oh, man! Even pouring molten glass on it doesn't make it shatter immediately. But give it a minute.
Some strong glass.
It is.
Or 4.
Oh man, that was cool! It was like,
The molten glass finally compromised the surface. And all that built-in stress broke up the entire sheet. But the remaining shards are relatively safe.
Because of that tension, when it does break, it breaks all the way out to the very edge, and it all breaks into these little bits. They make these nice little cubes that aren't nearly as dangerous as a big broken shard of glass.
The miracle of glass is made possible in part by the element silicon, the second most common element in the Earth's crust, after oxygen. Silicon atoms have 14 electrons arranged in 3 shells. Because the outermost shell has 4 electrons, silicon can share those to form up to 4 bonds with other atoms. But one thing that it doesn't do well is form a chain with other silicon atoms to create a compound with a silicon backbone. It's just too reactive. In water, the backbone easily falls apart. The element with the best ability to do that sits just above silicon. Carbon can also form up to 4 bonds with other atoms, but luckily it can also form strong bonds with other carbon atoms. The result is not only you and me and all life on Earth, but also a plethora of other molecules and materials that shape our lives and can even put a bounce in your step. First up, rubber. It turns out that more than half of the world's rubber ends up wrapped around the wheels of vehicles, motorcycles, trucks, and cars. So I've come to a place that's rolling in it. The Indianapolis Motor Speedway. It's 11 days away from the running of one of the most famous car races in the world, the Indy 500. The competing teams are here doing practice runs. And some end better than others. Before the teams hit the track, some fortunate fans get a taste of the race. They get to ride in a specially adapted 2-seater Indy car. At the wheel, the legendary champion, Mario Andretti. He's one of the most successful American drivers in the history of the sport. He's the only pro ever to win the Indianapolis 500, the Daytona 500, and the Formula One World Championship. And now, it's my turn. Imagine riding a roller coaster at over 180 miles an hour with no rails, flying around the curves while wondering why we're not smashing into the wall. I've had enough after a couple of laps. How do these drivers do 200 of them?
oh man, the G-forces are just indescribable. I mean, you're pressed against the side and then pressed against the back. And when he takes the curves, I mean, there's a concrete wall coming at you, just...
So what's the secret ingredient to staying alive out there? To find out, I head to the garage that supplies the tires in the weeks leading up to the Indy 500. In 2019, each team received 36 sets of tires for practice, qualifying, and the race. 6,000 tires in all. It's also a chance to talk to the expert himself.
What I was surprised at most was the lateral forces, obviously, as a layman. So is it the rubber that's keeping us from flying into that wall?
That's what it is. That's it. The tires are obviously the most important aspect of the race car. These are the babies you want to kiss after a run.
At speeds up to 230 miles an hour, a driver experiences about 5 Gs of force during the turns. That's more than what an astronaut experiences during a space launch. So you know the tires take a beating. Do you know enough about the chemistry to know what kinds of things they can do to the compounds? Like, what sorts of things do they add?
If they would tell me that, they would have to kill me.
Hopefully, that's not a blanket policy, because I've come to Akron, Ohio, looking for some answers. Harvey Firestone founded the Firestone Tire and Rubber Company here in 1900. Bridgestone Corporation bought it in 1988, becoming Bridgestone Firestone. This is one of its research facilities, and Laura Kosis is one of its scientists. According to her, it all starts with this.
I gotta say, this feels rubbery. And oh, man, it's also stinky.
Yep, so that's natural rubber.
Oh, this is what comes out of the tree.
Yep, so it comes out of the tree, we process it, and it turns into what you have in your hands right now.
Becomes this.
Yes.
Natural rubber begins as sticky, runny white liquid called latex. It's found in more than 2,000 plants, including dandelions. But most of the world's natural rubber comes from trees, like these, the Hevea brasiliensis, better known as the rubber tree. Natural latex is about 55% water, with particles of rubber suspended in it. And if you could zoom in to one of the particles, you'd see it's like a tangled bunch of spaghetti. Each noodle is a long molecular chain called a polymer.
To get to a polymer, you start with monomers, which is one chemical unit, and that's represented by these paper clips here.
This here is one chemical unit?
Yep, consider that one chemical unit.
Meaning what, a molecule?
Yep, one molecule.
So for natural rubber, what molecule are we talking about?
So if we're talking about isoprene.
Isoprene, okay.
Yes.
Here's what isoprene looks like. It's a molecule with 5 carbons bonded to each other and to 8 hydrogens. In natural rubber, isoprenes are bonded together, one after another, to make a chain, a polymer, just like the chain of paper clips Laura showed me.
Once you get to tens of thousands of these units linked together, you end up with natural rubber.
Oh, tens of thousands?
Yep.
Okay.
Tens of thousands.
In their natural state, the rubber polymer chains can become easily entangled as they coil up. But when you stretch them out, the chains straighten out and align themselves in the direction of the stretch. Let them go, and the molecules return back to their coiled up states, giving rubber its signature boinginess.
So if it's rubber, it should be a little boingy.
Yep, it's gonna bounce.
Ah! Okay, that's very boingy. I'm sure here at Bridgestone you use that as a chemical property, the boinginess.
Yes, very technical.
And, oh, sorry. Oh, man.
Natural rubber is often an ingredient in tires, but it's not the only one. Today, many tires include synthetic rubber, made out of other monomers not found in latex.
Oh-ho! I'm sensing more polymers.
Yes.
More chains of molecules. What do these represent?
So these are different configurations of polymers that we can make in our laboratory. Natural rubber is made of only one type of monomer. Here, we can use different types and bring them together with our chemistry.
And each way of linking them together produces different qualities in the tire that will result?
Yep, so maybe the amount of monomer can make a difference in the properties, how they're configured can make a difference, and that's basically what we do here, is find different ways of putting them together so that we can achieve the properties that we want.
Wow.
Natural rubber, synthetic rubber. Turns out there's even more that goes into tire rubber. Here in the test lab, technicians mix all the ingredients together, like carbon black and silica, which reinforce the tire. Another key ingredient is sulfur, element number 16 on the periodic table. The resulting blob then gets rolled into sheets, cut cut into squares for testing, and baked at high temperature in a process called vulcanization. Charles Goodyear discovered the process in 1839 when he accidentally spilled a mixture of rubber and sulfur on a stove. He named it after Vulcan, the Roman god of fire. Cooking the rubber-sulfur mixture causes the sulfur to chemically bond the rubber's polymer chains to each other, forming cross-links between them. Bill Nyora, Bridgestone's Director of Innovation, shows me the result. So this little bow tie, this was cut out of one of those squares before vulcanization.
It was.
And this is what rubber looks like after that vulcanization.
Correct.
So the only difference between these two is this one was superheated for a while.
Correct.
All right, and according to you, something property-wise has changed.
It has. Once you take the uncured one and stretch it.
All right, this guy, just pull it. Oh, wow.
What you'll feel are the polymer chains flowing apart. It's acting like a liquid. It's viscous.
It feels exactly like gum, stretching gum.
And when you release the force, you'll see that it's flowed apart and the energy that you put in has not been recovered and the piece has been permanently deformed.
I broke your rubber sample.
I'm okay with that.
With all the new ingredients, our unbaked tire mixture is far less boingy than the rubber I saw in Laura's lab. When you stretch it, the mixture's loosely coiled polymer strands slide past each other and keep on sliding. Only weak interactions hold the network of strands together, so under stress, it pulls apart. Okay, and then after vulcanization, same test?
Indeed.
Oh man, it's much harder to pull.
And when you release the force, you'll see that it's recovered its original shape, and that's a characteristic of elasticity.
Stretch out this vulcanized, interconnected web of strands, and instead of ripping apart, the network springs back to its original shape.
Right, it's a cross-section.
But as Bill shows me with cross-sections from different tires, vulcanization doesn't just connect up individual rubber molecules. It connects up everything in the whole tire mixture.
As we cure the tire, as we heat it, that vulcanization reaction not only cures the rubber within a compound, it cures across compounds to connect all of that into one unit. In the end, it's essentially one molecule.
The whole tire?
It is.
The whole tire is a molecule?
It is.
Well, how is that a molecule?
So a molecule is a collection of atoms that are chemically attached.
Yeah.
We've done that through polymerization. We've attached monomers to make polymers. And then through vulcanization, we've attached the polymers to make the finished product.
So I guess, therefore, since this is all connected, molecularly linked to molecularly linked, it is one giant molecule.
It's beautiful.
Now that I know just how much engineering goes into those giant tire-shaped molecules, I have a new appreciation for the rubber that keeps us all on the road. And for the people behind it, like Kara Adams, Director of Race Tire Engineering and Production for Bridgestone Firestone. She oversees the race tire operation, including Indy. Although interviewing her at the office turns out to be tough.
One of the things that you're trying to look at with a race car is aerodynamics. If you think about a tire, this is the only point of contact between the cars and the ground now. That was a very small 4-inch wide rim. So 4 inches wide.
That's what you get for trying to film at a racetrack.
Yes, exactly. So we move to a somewhat quieter place. We think of car racing as excitement and adrenaline, really cool. How much actual science is there to it?
Well, there's a lot of science and chemistry that actually goes in the tire. So we have engineers that work with physics to make sure the tires are strong enough. And then we have people that are really smart in chemistry, and they are actually able to design those tread compounds that are running at 240 miles per hour and adhering to the ground. It's really exciting.
So are you trying to tell me that the only thing
between Mario and me and certain death is chemistry?
Chemistry and physics, absolutely.
Both the natural rubber and synthetic rubber used in tires are elastomers, polymers with elastic properties. They allow tires to be both flexible and durable. Marvels of engineering. But they have their limits. So what if you need an elastomer that can hold it together no matter what you throw at it? Michael Tidd from the company Line-X has invited me here, a lift in a back lot in West Springfield, Massachusetts, to see an elastomer that can be a protective coating. The day begins with a tale of two pumpkins. Pumpkins seem like they already are blessed with a certain degree of protection.
Nature has provided a pretty good membrane, but I don't know if it was in the original design to drop it from 50 feet.
Well, let's do a scientific
we
test.
could always give it a try and see what happens.
On three, ready?
1,
2, 3. Well, no surprise here.
It's a squash vegetable and a floor wax.
That was the control of a uncoated pumpkin, as you would find them in nature, yes.
Now it's time for a pumpkin covered with Michael's protective Line-X coating.
I have to say, it feels a little bit like plastic.
It is a lot like plastic. It has characteristics of plastic. However, it is an elastomer, which means it can be stretched, but it will return to its original shape.
Let's see if this has any better effect. 1, 2, 3.
The Line-X coated pumpkin flexes to absorb the impact, then springs back into shape. We try a few more household objects.
This experiment is entitled When Pigs Fly. Can you guess what will happen to the egg when we drop it? The flower pot's last moments.
And I run a few comparisons myself. Finally, bringing out the big guns.
No way.
Okay, I get it. The stuff is tough. But what's going on inside that coating? Did the objects survive intact? Michael cuts open our dropped pumpkin to see the state of affairs.
It's pumpkin pudding.
A lot of damage.
So the pumpkin is gone, but the coating did just fine.
Correct.
But when would you care about not protecting the guts of something, but the outside is fine?
A lot of times we will put it on a membrane such as a wall or a floor where we're trying to protect what's on the other side.
Here's a test of that idea. This simulated car bomb blows down an exterior wall. But with a coating of Line-X on the outside and the inside of the wall, it becomes more of a dust-up. So what is this stuff? Well, there's more than one flavor of Line-X, but the coating on our power pumpkins is the result of a reaction between two ingredients. The first is a highly reactive molecule. At each end of its carbon backbone, there's a nitrogen, carbon, and oxygen group called an isocyanate that acts like a hook to lock onto the second chemical ingredient. It's a polyamine, a member of a chemical group called resins. Line-X heats the two ingredients and feeds them under pressure to this sprayer which mixes them just as they exit. Immediately, the first ingredient hooks on to part of the resin, and all those linkages create long and tangled polymer chains similar to rubber, so that they're flexible but also much tougher. The resulting elastomer is called a polyurea, a cousin to the more familiar polyurethanes. So that's the general idea, though they tweak the chemistry for different applications. Most of Line-X's consumer business is spray-on truck bed liners, not so much for protecting produce or making kids' toys last forever. The main ingredients for Line-X and synthetic rubber come from fossil fuels, like refined crude oil. When we pump oil from the ground, it's a rich soup of molecules built around that Tinker Toy wonder element, carbon. They come in chains, rings, trees, and other shapes. Refining separates those molecules by kind, and in some cases breaks up bigger ones, turning them into smaller, more useful molecules like gasoline. Refining also supplies industry with the basic building blocks for another group of synthetic polymers that came to dominate our way of life in the 20th century: plastics. Today, plastic is everywhere. You can find it in tea bags, ribbon, the inside of paper coffee cups, sunscreen, toothpaste, sponges, most clothing, the fish you eat, and even salt. Malika Jeffries-L plays with the molecular building blocks of plastic for a living. She's a polymer chemist at Boston University. So clearly, there's all kinds of different plastics. But is there something that unites them all, that makes a plastic a plastic?
Plastics are a subset of polymers in that they're known not just for having their macromolecular structure, but the processing and mechanical properties that come from as a result of that structure.
Like bendiness and...
Exactly,
strength.
exactly. Strength, exactly. Strength, flexibility, rigidity would be another property.
Like rubber, all plastics are polymers, long molecules made up of subunits called monomers. What makes each of these polymer-based materials distinct are the combinations of the different monomers used to make them.
For example, this is actually really hard and rigid, and one of the units in here is styrene, and this is polystyrene.
Not hard and rigid at all.
Not hard and rigid at all, but when you blend in the other molecules, you get different properties.
Wow. But it's not all chemistry. Processing can turn the same plastic into very different products.
These were actually molded and blown into this bottle shape. And in this case, really small fibers were spun from the polymer and then processed to make this.
And it comes out soft and comfortable.
Comes out soft and comfortable.
Our age of plastics isn't very old. It was this guy, Leo Baekeland, who gets credit for the first fully synthetic plastic. He called it Bakelite. And by the 1920s, it had become a big hit in all kinds of products, from radios to kitchenware to kids' toys, and coming in a variety of colors. Malika has offered to whip up some of this landmark plastic. It's made from two monomers: phenol, a ring of 6 carbon atoms bonded to 5 hydrogens, and an oxygen bonded to a hydrogen, and formaldehyde, 1 carbon atom bonded to 2 hydrogens and double bonded to an oxygen. After dissolving the solid phenol into the formaldehyde solution, Malika adds 2 acids to start up the process. Then we wait.
There should kind of be this aha moment, and it should just go.
Are you saying it's going to harden?
Yeah, it should get cloudy, and polymer should come crashing out. I feel like it's getting pinker, which is an indication that the chemistry's changing.
Oh, did you see that? Like instantaneously. Right before our eyes, the phenol and formaldehyde molecules link up, giving off water molecules while creating long polymer chains. You made plastic! Look at that. Genuine, crusty, hard plastic.
So this is an example of a thermoset plastic. Once it's set into place with heat, you can't reform it or reshape it with additional heat.
Oh, okay. So unlike a plastic drink bottle,
That's right.
you can't melt this down and reform it into something else.
No.
This is Bakelite now and forever.
That's stuck like that forever. Yep.
In a thermoset plastic like Bakelite, the bonds between the polymer chains are extremely strong. By the time you've applied enough heat to break them, the chains themselves have decomposed. So you can't remelt thermoset plastics or reshape them for recycling. But not all plastics are thermoset. There's nylon, the first commercially successful plastic that wasn't. It came to public attention at the 1939 World's Fair as a substitute for silk in women's stockings. And its importance grew during World War II. At the time, the main source of silk for parachutes was America's enemy, Japan, so the military recruited nylon as a replacement. Malika offers me some first-hand experience making nylon. If you wanted to make nylon, don't you need like a factory?
Well, if you want to make a lot of nylon, yeah, then you're going to need a factory. But if we're just going to do a demo, we're going to make a little bit of nylon, and we can do it in a little beaker.
All right, like for mouse stockings.
Yes, exactly. To do this, we're going to mix together 2 chemicals.
There are lots of variations on nylon. Our 2 key components will be 2 molecules that are simpler than they sound: hexamethylene diamine and adipoyl chloride. Since they each have a 6-carbon chain, we're making what's called nylon 6,6.
So the first thing we're going to do is we're going to add the hexamethylene diamine.
So mostly colored water.
Mostly colored water with some cool organics in there.
All right.
And then we're going to add our organic layer of the adipoyl chloride solution. And because the density of this is less than that of the water, it should float on the surface of the water.
Kind of like oil and vinegar. Where the 2 liquids meet, the molecules of the hexamethylene diamine and adipoyl chloride link up, one after another, releasing hydrogen chloride as a gas. Malika gives me the honor of pulling the newborn nylon polymer out of the beaker. And as more of the 2 liquids come into contact, they make more nylon. Yeah, you have a ladder, Malika?
There you go. Look
at that.
Yes.
Freshly baked, free-range nylon. Amazingly, this really is a junior version of how bulk nylon is manufactured. All right, anyone need stockings? Unlike Bakelite, nylon is an example of a thermoplastic, which we can reheat and reform. That's the basis of some plastic recycling.
You know, get the...
Malika wants to show me one more example. And this time, what are we gonna make?
So for this demonstration, I thought I would show you how we make polyurethane foams.
And what do we use polyurethane foam for in the world?
Polyurethane is used in like seat cushions and also insulations. You think about like blown foam and things like that.
Oh yeah, E.T. blown foam. Yeah, I remember that. Yeah. There are 2 key reactants. First up is a type of molecule with an oxygen-hydrogen hook at either end. Aside from its role in polyurethanes, this one shows up in paintballs and laxatives too. The other reactant we've already met at Linex, that carbon-backboned isocyanate molecule with the nitrogen-carbon-oxygen hooks at either end.
We stir this together. And so you can already see it's starting to react because it's starting to get milky and it's starting to grow inside. You can see it's rising up a little bit.
The 2 molecules begin to link up to form a polyurethane polymer. At the same time, one ingredient also reacts with some water, generating carbon dioxide gas. That's what causes the bubbling, and ultimately the foam, when the polyurethane grows rigid. I know I'm tacky, but oh, and the cup's entombed inside there.
The cup is gone.
Yeah. Pretty cool, but it's just a start. Because when in foam, do as the foamans do.
There we go.
Years of snowman training. We'll open a 529 plan, we'll buy some diapers.
Nothing but the best for you. Here's your smile.
At this point,
Polycarbonate,
you're probably getting the idea
polyethylene terephthalate, PETE,
that there are lots of different plastics,
polyvinyl chloride, PVC.
each made out of polymers
These are examples of polyamides, commercially known as nylon.
constructed sort of the same way,
Polystyrene,
but out of different subunits
polypropylene, PP.
to obtain very different material properties.
Low density polyethylene, LDPE.
And then if you start throwing in additives and fillers,
Polyvinyl alcohol, PVA.
like colorants,
High density polyethylene, HDPE.
flame retardants, glass or carbon fibers,
Polymethyl methacrylate, PMMA.
you end up with tens of thousands of grades of plastic,
Polyoxymethylene, POM.
each tailored for a specific purpose, which has created the problem. What do we do with them when that job is finished? Mostly, we throw them out. 91% of all the plastic we make ends up in landfills, or burned, or just escapes into the environment. The remaining 9% is recycled. But first, the plastic has to be carefully separated by type, those recycling number symbols. Any mix-up there can contaminate an otherwise reusable plastic, rendering it worthless. And there aren't many places willing to do that separating work. In 2018, China stopped accepting shipments of bulk unsorted plastic from the US or anywhere else in the world. With the economics of recycling in turmoil, lately the discussion has shifted to single-use plastics, about half of all the plastic we produce. Much of it is food-related. To learn more, I traveled to the University of Georgia to meet Jason Laughlin, a chemistry professor and the director of its New Materials Institute. Well, thanks for meeting me here, Jason. I brought you breakfast.
All right.
And, well, breakfast and a bag of single-use problems.
This is called a clamshell container. Less than 1% of all polystyrene is recycled globally. If this makes its way into the landfill, which is exactly where it'll go, it'll persist there forever. We have a plastic straw. It'll stay there for hundreds, if not thousands of years. Is that really a way to design packaging, to have a material that you use for 10 seconds, and then it goes to a landfill for 1,000 years?
Even packaging that looks recyclable, like paper takeout containers, may not be because, well, they have to hold food.
If you put food into a paper towel, what happens to it?
It's gonna get soggy and fall apart.
Exactly. So in order to make this a takeout container, we have to coat it with plastic. It essentially prohibits our ability to recycle it.
Wow. So is there any solution to that problem?
So here's just an example. If you pull the film off that plastic, this is about what it looks like. But this film is made out of a material called PHA.
PHAs, polyhydroxyalkanoates, are a type of plastic produced from polymers harvested from certain bacteria. For the bacteria, the polymers are essentially kind of like fat, a way to store energy. But because they come from bacteria, PHAs have a huge advantage. they're completely biodegradable. Researchers in Jason's lab are among several scientists and companies around the world developing a PHA-based coating that could replace the traditional plastics that often make our takeout boxes unrecyclable. Although the cost of PHAs still needs to come down to be competitive. And finally, what does Jason think about that eco-friendly looking green bag I brought breakfast in?
This is a great example of some absolute greenwashing. Biodegradable. You see it in big bold claims. If you read the fine print, it says 49.28% biodegradation in 900 days under non-typical conditions. No evidence of further biodegradation.
Come on!
I mean,
sounds like a total scam. But look at the size of the green leaves. That makes me feel good about myself. It has a leaf on it.
This is simply adding to the confusion of people like yourself, people in the general public that want to do the right thing. This makes it really difficult to know exactly what to do.
Oh!
When it comes to creating new materials, we may be the victims of our own success.
Oh, it was like...
We've invented some that are useful and so durable that they last more than a human lifetime. And now we're drowning in them. But attitudes are changing, with engineers and chemists harnessing biology to combat the problem. In the end, the human ingenuity that helped create the current crisis may help solve it as well.
The only thing between me and certain death is chemistry?
As we move beyond the elements.